Oh, welcome. It's a lesson video on differentiating parametric expressions. It's something we've seen differentiation before, and we've seen parametric equations before, but now we're going to try and join these two ideas together. So let's start off. It says, first of all, find and sketch the Cartesian equation of this curve. Now, you can see we've got it written in parametric equations. I'm wondering whether or not you could possibly try to rearrange that so you get a parametric equation, and then we can, a Cartesian equation, and then we can try and work out what it looks like. So try and get rid of the t, or get rid of t, write it as t equals, and then sub that into your second equation. And likewise here, we actually had a special technique with cosines and sines. See if you can remember to do that. I'm going to pause the video now, and I want you to see if you can get the Cartesian equations for yourself. Okay then, so I'm going to do it now, and whether you've done it or not I don't know, but hopefully you have. So on this one I think I'd write x minus 1 equals 2t, and that allows me to write t equals the x minus 1 over 2, and then subbing it into this I get y equals 2 plus 3 over 2 x minus 1. I might want to just tidy it up a bit. I reckon that's y equals 3 over 2x. Now that's minus 3 over 2, but plus a 2. I reckon plus a half. I don't know if that's right or wrong, but that's a straight line graph. It's a straight line graph that basically looks something like this, where it crosses at half. There you go. I'm going to say that's half now. With a gradient of 1.5, so it's going to look something like that. Allowing for my dodgy line crossing there. I'm not sure if it comes up with both answers together. I'll just carry on. On this one, you should have squared both. We've seen already how to do this. You square the first one. X squared is 16 cos squared theta. That allows you to write that x squared over 16 as cos squared. And on the second one, you write that y squared is 4 sine squared. So you can simply say that y squared over 4 equals sine squared. And of course we know that sine squared and cos squared added together give us 1. So that basically lets me write x squared over 16. 16 plus y squared over 4 equals 1. Now that's normally how it's written. Now that is an ellipse. Again, what's it look like? Well, the x is over 16, so if you square root the 16 you get 4. So basically there's minus 4 there and 4 here. Square root the 4 you get 2, so on the y-axis you get 2 and minus 2. Let's see if I've got those right. This is y equals a half plus 3 over 2x. The equation is right, and that's a straight line. And the equation is right, and that's an ellipse. So everything looking good so far. So hopefully you understood that. Now this is definitely new. We've not done this before. Now one of the reasons for doing parametrics is because it makes differentiation of certain types of functions easier. Not always, sometimes it's harder, but there are times where it's definitely better using parametric equations. So suppose the parameter is t. This is the chain rule. We've seen this chain rule before, but now we've tended to use it on examples like this. So if I just do a quick example, y equals, and I'm just going to write, I don't know, the sine of 3x plus 5. So totally made up, but we know that we can write u. This is what the chain rule really is. You write u is 3x plus 5. And of course that allows me to find dy by dx. Now the trick with dy by dx is to use something similar to this over here. I'm going to use dy by du, du by dx. And if I differentiate the y, well first of all I've got to rewrite the y, because I've said this is u, so let's write it as sine of u. And therefore you'll notice it says dy by du. It's the right thing I'm doing. Dy by du, you should realise becomes cos u. So that's cos u. Now I've got to times it. This means times by du by dx, and du by dx is what happens when I differentiate that. Du by dx, and that's 3. So my answer is 3 cos u. Now I don't like leaving it like that. I want to get rid of that u. 3 cos. Now u was 3x plus 5. Now that is what is the posh way of doing it. In actual fact, I've taught you not to do any of that. I've taught you just to pretend it's sine of x, in which case it comes cos of x, but then you have to bring that 3 to the front, I've said. But this is the reason why, because it's really the chain rule. And we're going to use this chain rule today using differentiation of parametrics. There's another way some people prefer to think of it. I personally don't, but you might see that in some books or whatever if you read them. So let's have a go at a question. It says use differentiation to find the gradient of the point at 8,8 on this curve given by this. Okay, so I want dy by dx because it says find the gradient. The gradient dy by dx can be found by using the chain rule, dy by dt by dt by dx. And it should be a little times in the middle perhaps. So what's dy by dt and dt by dx? Well, first of all, I can quite easily go from there and say that dx by dt. Notice it says x equals, so I write dx by dt equals. If I differentiate, I get 4t. And again, from this one, I get dy. It says y equals, so I get dy by dt. If I differentiate 4t, I just get 4. So dy by dx, it says it equals dy by dt. Well, I know that's 4. Times by dt by dx. And I've got a slight problem. I haven't got dt by dx, but I have got dx by dt. It's the upside down version of it. So this becomes 1 over 4t. And if you find dx by dt, you can turn it upside down. You can always turn it upside down to get dt by dx. And notice those 4's cancel, and the answer is 1 over t. Now, 1 over t doesn't quite help me because I need to know what x is. So one way of doing it perhaps is to look at this and say, hang on a bit, I'm just going to write it over here. T, if I rearrange this, is y over 4. So I've got a way now of finding this out. So I can now write dy by dx equals, and I could have used the other one if I'd wanted to. As it happened, it didn't matter because I knew both my x is 8 and my y value is 8 as well. So I could use either. So dy by dx, well, let's just go here. My 8 is what my y value is. So t is 8 over 4, which is 2. So now I know t, dy by dx is 1 over 2. There you go, it's a half. Let's see if I agree with myself. Gradient is half, there you go. So here's another question. Find the equation of the tangent to the ellipse. Now this is harder. It involves a bit more maths. Let's have a go at it. Find the equation of the tangent to the ellipse. X is 3 cos theta, y is 2 sin theta. At some point. So let's worry about that all in a bit. Let's first of all find dy by dx. So dy by dx. Now we use the parameter. This time the parameter is theta. So I shall write dy by d theta by dx. And for each one of these I shall find the differentiation. Dx by d theta. Well, you should remember that sine, cos, minus cos. So if I differentiate that cos, it goes minus sine. So I reckon this is minus 3 sine theta. Let's do the same over here. We'll do dy by d theta. And dy by d theta, off sine comes cos. So this becomes 2 cos theta. So let's write these down. Dy by d theta is 2 cos theta. And it's times by, now again it says d theta by dx. I know dx by d theta. So that's 1 over minus 3 sine theta. So it's not very nice. It's minus 2/3 of, well, I could write 1 over cot really, or 1 over tan, because that's what it is. So it could be written as cos over sine. But you should spot that that's like an upside down version of tan. So I could write it as minus 3 tan theta on the bottom, or I could write it as minus 2/3 of cot theta. I don't mind any of all of those, all right. And it doesn't really matter, because all I'm going to do is substitute this theta equals quarter pi into it. So in that sense, it might be better to use this one. So I'm going to write when theta equals a quarter pi. Great thing about a quarter pi, a tan of a quarter pi is tan of 45 degrees, which is 1. So therefore this implies that dy by dx is minus 2/3 times by that 1 on the bottom, which won't change it at all. It's minus 2/3. How do I find the equation of the tangent? Well, I use this old equation. y minus y1 equals mx minus x1. What information do I need? Well, I need to know what x is. This will be my x1. x1 is 3 cos of pi by 4. At this point, pi by 4. Now, cos of pi by 4 is root 2 over 2, I think. So this, let's go menu 1. 3 cos. I'm just trying to check if I'm in degrees or radians. I'm in radians, good. Of pi by 4. I get 3 root 2 over 2, good, but it's always good to check. Especially in the exam, you don't want to make daft mistakes. And y1 is the same thing. It's 2 sine pi by 4. And again, sine of pi by 4 is root 2 over 2 again. So this is like 2 root 2 over 2. Or I can just call it root 2. So this is y minus root 2 equals m, which is minus 2/3, x minus 3 root 2 over 2. So if I just tidy this up, I reckon I get y, well, I'm going to move the 3 over, 3y minus 3 root 2 equals minus 2x plus 3 root 2. How about 2x then, plus 3y equals 6 root 2. I'm not sure if that's right or wrong, I shall check. Getting there. Yes, got it. I'll go try this one and see if we can quickly do it. Find dy by dx for the curve given by this. So again, dx by dt is my first thing I'm going to do, equals 2. Well, this, of course, is t to the minus 1. So when I find dy by dt, I'll get minus t to the minus 2, which is minus 1 over t squared. Okay, I've done that. So now I've got this, of course, I can now use my dy by dx equals dy by dt, dt by dx. So dy by dt, what was that? Is minus 1 over t squared. Times by dt by dx. Be careful, remember dx by dt is 2, therefore dt by dx is 1 over 2. So this is minus 1 over 2t squared. Of course, I've got an answer I'm heading for here, which is always nice. Now, look, I need to get t. So x equals 2t, and they're told about this point here, and it says that the x value is 4. So if x equals 2t, 4 equals 2t, I reckon that probably tells me that t equals 2. So I know t is 2. I need, therefore, to substitute in. So the m is equal, when t is 2, minus 1 over 2 times 2 squared, which I reckon is minus an eighth. Now that's a bit rubbish, that, because that's m, that's for the tangent, but they want the normal, so the gradient really turn upside down and change the sign, 8. So I can do y minus y1 equals m x minus x1. It was a half, equals m, which I reckon is 8, x minus, it was 4. So multiply everything out on the right hand side, 1 minus a half equals 8x minus 32. I don't really like the fact that it's got a half, so I'm going to double everything. 2y minus 1 is 16x minus 64. And I reckon if I put the letters on the right, I get 16x minus 2y. Move that over there, gives me equals 63. And yeah, that therefore, I reckon I've shown that. Make sure you write it out just to finish with. Just you get the same thing. Yeah, that works. And that's the final equation. So look, we're finished and it's perfect timing. We'll do exercise 12C in class. I've suggested don't do question 5 or 6, but other than that, let's have a go.